Every time a rocket like the Starship or the Vulcan ignites, it defies the very laws of gravity. But the real miracle isn't just the flight, it is the chemistry. To push 5,000 tons of steel into orbit, you need more than just fire. You need liquid fire. In the world of aerospace, we call this cryogenic propellant. Today, we are going behind the concrete walls of the world's most advanced fuel factories. We are exploring the high-pressure, ultra-cold world of liquid oxygen and liquid methane. This isn't just fuel, it's an industrial masterpiece. And this is how it's made this way. The journey begins not in a mine, but in the very air you are breathing right now. Our atmosphere is a treasure trove of energy, but it's spread thin. To gather the thousands of tons of oxygen needed for a single mission, we need massive scale. These are air separation units, or ESUs. Giant intake fans, some as large as a house, pull in millions of cubic feet of air every hour. But the air is dirty. It contains dust, water vapor, and carbon dioxide. To a rocket engine, these are contaminants that lead to catastrophic failure. First, the air must be compressed. Huge multi-stage centrifugal compressors spin at thousands of RPMs, squeezing the air until it heats up to over 100 degrees Celsius. This high-pressure air is then moved through pre-cooling units. Imagine the power required to squeeze the atmosphere itself. But compression is only half the battle. We need to strip away the enemies of rocket fuel. Inside these silver columns are molecular sieves. These are the unsung heroes of the factory. Think of them as chemical gates. They are filled with zeolite porous materials that act like a microscopic maze. As the compressed air rushes through, water molecules and CO2 are physically trapped in the pores, while the nitrogen and oxygen pass through. If even a tiny fraction of water remained, it would turn into an ice bullet at cryogenic temperatures, shattering the high-speed turbopump of the rocket engine. Now, the clean air enters the heart of the factory, the cold box. This is a massive, insulated skyscraper of steel. Inside, we use the Joule-Thomson effect. By allowing the highly compressed gas to rapidly expand through a tiny valve, the temperature plummets. It's a physical phenomenon where gas loses energy as it expands. We repeat this cycle until we hit the magic number, minus 183 degrees Celsius. At this temperature, the air stops being a gas. It collapses into a beautiful, glowing pale blue liquid. This is liquid oxygen, or LOX, but we aren't done. The liquid is still a mixture of oxygen and nitrogen. To separate them, we use fractional distillation. Inside a tower hundreds of feet tall, we use the different boiling points of gases. Nitrogen boils at a lower temperature than oxygen, so it rises to the top as a gas, while the pure liquid oxygen pools at the bottom. This process is so precise that we can achieve 99.99% purity. Oxygen is the oxidizer, but we still need the fuel. For the next generation of rockets, that fuel is liquid methane. Unlike the kerosene used in the 1960s, methane is clean-burning and can actually be manufactured on other planets like Mars. We take natural gas from pipelines and put it through a similar cryogenic process. We chill it to minus 161 degrees Celsius. In its liquid state, methane is 600 times more dense than its gas form. This density is what allows a rocket to carry enough energy to leave the planet. Once created, these liquids want to boil away instantly. To stop them, we build the world's most advanced thermos flasks. These are vacuum-insulated tanks. They consist of an inner stainless steel tank and an outer carbon steel shell. In between the two layers, we create a total vacuum and fill it with perlite, a volcanic glass that blocks all heat transfer. This cold chain must never be broken. From the factory to the tanker truck, and finally to the rocket's belly, the fuel must stay at hundreds of degrees below zero. When the countdown reaches zero, these two liquids, oxygen and methane, finally meet inside the combustion chamber. The blue flame you see isn't just a fire. It's the result of months of industrial processing, molecular filtering, and cryogenic engineering. It is the invisible force that makes humanity a multiplanetary species. From the air in our lungs to the fire in the stars, this is the incredible journey of rocket fuel. And now you know, It was all made this way.